Today is our concluding lecture, and I'll talk about decision trees and interesting outcomes of decision tree learning. We already discussed bagging and boosting in the last class and also kind of revisited them in the lab session. So bagging and boosting also were provided as a motivation for decision trees. And just to recap, we said that bagging benefits, well, to some extent boosting also benefits from low bias base learner. So low bias basically means that the base learner has enough flexibility. Very simply, we mean flexible base learner. And it turns out that decision tree is one natural choice. What decision trees do is they consider splitting feature at a time, basically making a decision on a feature at a time. So that's where the notion of a tree comes. So let's say this is a feature phi I, and phi I can have values vi1 to vij. Right? So this is a generic index for the feature values. So on every feature you split on some value, and for each branch that you take you can further pick some other feature. Okay, so phi I prime, phi I double prime, so some other, okay, I'll call it phi k, phi p, or so on, right? So keep splitting on features one at a time, and potentially because the space is very large, the space of trees, the choices of features to split on at every node is very large, you have very low bias. Okay. Obviously that makes the learning problem also slightly tricky. So therefore you do bagging around decision tree, because this would be low bias but it might have high variance. So the apprehension is that the bias is low but variance might be high. And a reason for the high variance is that the feature sequence that you adopt for splitting might actually depend a lot on the data set, might depend on the way you have scanned the data set, right? So there are too many variations that determine the feature sequence. There's a feature sequence here you're talking about. So feature sequence for splitting is sensitive to the choice of the data set. So let's kind of discuss this in slight detail. We'll talk about classification using decision trees, though some of this discussion will naturally also follow for regression. So when we talk of regression, you'll have to keep in mind two things, that features phi I, that's true even with classification, phi I could be continuous valued. So when you talk of feature splitting, what does that mean? And the other is the target is continuous, target dependent random variable. some more notation. Let me begin with the simplest idea called a decision stump. Okay. So the idea behind your decision stump, very much like your cricket stump, right, is that you just take one attribute. Let's say I want to develop a decision stump for detecting spam emails. So I'll say if email contains click here, then spam. Okay. So this is a simple decision stump, just one. Think of decision stump as simple one rule. Single rule, not a composite rule. Simple non-composite rule. Right, this is a decision stump. Or you can also think of this step function on individual features. You could say this is one decision stump. You could say if temperature less than 20 degrees, then you should go out and play tennis. Let's say the choice to be made is whether you should play tennis or not. So if the temperature is less than 20 degrees, go out and play tennis. Right, so it's also called a step function. I mean, it could be a step function. Which means if it's greater than 20 degrees, you don't play tennis. Okay, on individual features. And you could think of the decision tree as a cascade of decision stumps. Okay, so if for the first example, we can say if email contains click here is spam, and let's say there's another decision stump saying if email contains you are invited, right? So other feature. So again, this might be indicative of spam. Now think of composing these two. So this composition corresponds to a composition of decision stumps in a particular way gives you decision tree. So cascade and the cascade is in a particular way, and we'll talk about that. So this is going to be our canonical example, whether to play tennis or not. Each row here corresponds to a day, an instance, and based on outlook, the temperature, the humidity and the wind, a person decides whether to play tennis or not. This has been recorded, and outlook can take some specific values, for example whether it's sunny, whether it's overcast, whether it's rainy. On the other hand, temperature could be hot, mild or cool. Humidity could be high, normal, and wind could be weak or strong. So two values that wind can take, humidity can take two values, temperature can take two values, and outlook can take three values. Okay. And suppose I want to now build a decision tree. Okay, so I can start with a simple decision stump which says that, well, let's try and build one. I would like you to build one, right? So I want you to build a cascade of decision stumps. For this data set, try and build a decision tree. So what would you be doing? You would pick some feature to split on to begin with. So is there a feature that is very indicative of play tennis here? When I say feature comma value. What are you looking for when you pick the feature to split on? So you'll have phi I and you want Vi1 and Vi2, say the two values on which you split. It could be multiple values, 3 values also. Or you could have a query with saying, is Outlook equal to Sunny? Do something. So that's also possible. You can have a binary split. But let's say we have multi-valued split. So what would you split on to begin with? So the decision to be made is whether to play tennis or not. This is the dependent variable of interest. And you're looking at, let's call these phi 1, phi 2, phi 3, phi 4. So you are trying to associate the dependent variable with one of the independent variables in terms of how correlated, how strongly does the value of a phi determine the dependent variable. So where would you begin? You could do a simple counting, right? You could just say count for each phi I and for each Vij, right, that phi I equals Vij. Estimate the count of, okay, for each class Ck, you could look at the count of phi I equals Vij, comma Ck, and pick that which has the maximum value. Would that be a good idea? So I'm just suggesting a simple heuristic. I'm saying for each value that a feature can take, right, and for each class, count the number of times they co-occur and pick phi I to split with max count. Okay, let's just get these counts quickly. So in this figure, so count of, so let's begin with phi 1. Phi 1 has 2 values, sunny, 3 values, sunny, overcast and rain. Sunny, so what is the count of sunny and play tennis, say whether to play tennis or not, right? So how often does sunny occur with play tennis? Twice? Is that correct? How often does overcast occur with play tennis? Okay, how often does sunny occur with not playing tennis? Huh? Thrice? So I'm putting these numbers here. How often does overcast occur with playing tennis? 4. And with not playing tennis, how often does overcast occur? Huh? 0. And the third value, which is rain, how often does rain occur with playing tennis? 3. And no? Twice. Okay. So I did this for phi 1. Let's get similar numbers for phi 2. Phi 2 is temperature, hot, mild or cool. It takes 3 values. Hot, mild and cool. So again give me the counts. Hot, yes. How often does, is it that the temperature is hot whereas the person did play tennis even when the temperature was hot? Twice? Okay. with mild, with no, how often was the temperature hot and the person did not play tennis? Twice again. Others can verify numbers. With mild and cold, let's get this table. Like, I would appreciate everyone writes this table down. With mild, 4 times played, and how many times did not play? Twice. And cool, thrice he played. Once did not play. We are almost there. So we are done with 2 features. Phi 3. Let's get those numbers. So phi 3 is humidity, high or normal. That's it. High or normal. Only 2 values. How often is that? With high, the person decided, high humidity, the person still played. 3, and did not play? 3. 4. Okay. I'll just trust your count. And with normal humidity, 6 times played, and then phi 4 finally. What is that? Wind, weak and strong. What are the counts? 6 times played, 2 times, twice did not play. And with strong wind, okay, so what you expect is that the sum total of yes for every phi should be the same, right? 9, 4 plus 3, 7 plus 2, 9, 9, 9, 9. So basically all you are doing is just dividing the yes amongst the different values of phi 1, right? You did this for phi 2, for phi 3, all of this sum to each of this is 9. And the sum of all the no's for each feature is exactly 5, right? So just verification. So you just divide it up, that's it. Now tell me which feature will you use for splitting this? Let's say we discard the other table, just use this observation.
Binary split means that for those features which have 3, you put 2 of them in 1. Is that right?
If you did a binary split, you will say if is the phi feature phi I equal to Vij. But let's not get into binary. Let's look at the splitting on these 3 different values or 2 different values. We'll get to other splittings.
You said binary.
No, I am suggesting split based on each value. Okay, so split based on phi I equals Vij. So I want you to tell me which should be the first phi based on which I have 2 or 3 way split. Right? These 2 cases is 2 way split. In these 2 cases there is 3 way split. What should be the next phi to split on, and so on. You have to, and then you have to choose another phi to split on each branch, and this goes on, right? So just give me the first phi. Which would you split on? What do you expect the phi to do? The split to do with respect to the data set? Should the class distribution in each branch be skewed, be uniform? What do you expect? Okay, let me just start with the first phi. Okay, first phi. If I start with phi 1 to split on phi 1 SOR, then what happens? The distribution is 2, 3, 2 yes and 3 no. 4 yes and 0 no's, 3 yes and 2 no's. Okay, let's do this. So if it's phi 1, my split would have been into S, O and R. Okay, and S would have become 2 yes. Okay, this is yes. These are no's. Okay, so 2 yes and 3 no's. 2 yes and 3 no's. Is that clear? With O it would have been 4, 0. R would have been 3, 2. Let's just compare two features, okay. Let me compare phi 1 and phi 2 for the time being. I'll do the same thing. H, M, C. These are the three two, 2, 4, 2, 3, 1. So between phi 1 and phi 2, what looks like a better split? Better feature to split on? So why are some of you suggesting phi 1? Yes? So some of you might be looking at this, right? I mean, look at this. There's a bit of more skew here. 4, 0. 3, 2 is skewed, 3, 2 is skewed. Here 2, 2 is very uniform. Compared to this 4, 0, this is 4, 2 here. Well, this one is the only one that's showing slightly more skew. The total instances of skew here is 3, with maybe slightly more weightage here. Here there is only one instance of skew, which is probably not as much as 4, 0 itself is. Is that one criterion you'll use? But then somebody may ask, okay, what about phi 3? Phi 3 has only two-way split, it's not even three-way split. How do you compare a two-way split against a three-way split? Okay, so we'll get to that in a, so I will defer phi 3 and phi 4 because that will bring up another dimension of splitting. But let's try and list down what we observe. Okay, so the first thing we want is that the data skew before splitting and the data skew after splitting, which of them should be more skewed, before or after? After, right? So this data here had some distribution of yes and no, C1, C2, and this had some skew. Ideally this was not very skewed. And after splitting, I'll just do one level of splitting now. After splitting, my skew of C1, C2 look like this or this. Okay. Now we are going to give a name to this skew. Data skew, you could also call it purity. What I meant is, if it's very skewed, that means there is some clear distinction between classes, right? So I'm going to call skew as purity. Purity means there is a clear indication which class dominates. We'll call it purity. So data skew after splitting should be greater than data skew before splitting. This is one requirement. And coming to this example, let's look at the data skew before splitting. It was the total yes at the top was 9, the total no was 5, right? We said 9 and 5 each. 5, 9. Now, since the data skew before splitting is the same in both phi1 and phi2, we were only discussing about the skew after splitting. But as we progress at different nodes, we may find that before and after you are really comparing different things. Okay, so let's continue this discussion and bring up another issue once we have nailed this down. Okay, so I really don't need that extensive table right now because we have this table. Okay, so this table is a good enough summary of what the other table had. Okay, so what we are going to do is keep deciding on splitting attributes. Okay, so somehow we chose the first splitting attribute here to be outlook, the first feature, and humidity was chosen to be, so humidity was which feature? Phi 3. Wind was strong weak, right? Phi 4. So this turned out to be one decision tree that you could build, and as expected we chose phi 1 to begin with, but then the question will be, okay, why did we choose phi 3 next? Why did we choose phi 4? Why did we choose phi 3 for the left branch, phi 4 for the rightmost branch, and in fact for the middle branch we did not choose any feature at all? So basically look at this, right? We are saying that sunny 2 3, overcast 4 0. Do you need to further along this branch further split? This is pure. This is a pure distribution, because 4 0 means everything belongs to one class. So you see, purity makes sense. So the more pure you are already, the less the need to further split. Okay, that's the second observation. Higher the purity, less the need to split. Do you agree with this observation? Higher the purity means higher the skew. Now, this was the data before I split, right? This is a view of the data before any split. But now, moment I choose phi 1 to be my first feature to split, will this table be useful anymore if I choose phi 1? No? This table itself, I mean, I'll have to further refine the table. Okay. So, what we'll also do is associate the data itself. So, here is the data before the split, and now this phi 1 had 3 values: V11 which was sunny, V12 which was overcast, and V13 which is rainy. Sunny, overcast and rainy, right? These are 3 attributes: V11, V12, V13. And along each branch, now I have further refined my data, all those instances which have that, which satisfy that. So I will call this DV11, DV12, DV13. So the data is now itself been refined along the 3 branches, and so on. Okay, we'll only be interested in what the previous state was on the next state is. So this is a decision tree representation. Each internal node tests an attribute, each branch corresponds to attribute value, and each leaf node assigns a classification. Okay, so you are testing some attribute phi I, and then each branch tests corresponds to an attribute value Vij, and then it might happen, like in the case of the first one, outlook, that some branches are just leaves, right, which is basically because they are very pure. Okay, so leaf node, the concept of a leaf node is basically a pure node. A node with high purity. Okay, so now I mean there are some more standard examples sitting here. You can think of how you would represent each of these. Yes. The second point, higher the purity, less is the need to split.
But even if it's slightly impure, like there is one node and we have to split.
So his question is, why don't we say that only 100% purity means you will not split? Why are we talking about anything less than 100% purity as not deserving to be split? And the answer you will see soon. See, the whole process, as we have seen, a little bit greedy. We are very myopic, and it should not be that we are, no, as I say, penny wise pound foolish. We may start fighting for small shillings. Oh, 100 example ठीक है, एक example को nail करना है मुझे. For that one example out of 101 examples, right? Imagine this was 400 and just 10. Now, for the sake of this 10 guys, should I actually have a new split? What might happen if I go for 100% purity all the time?
Too much implementation
Cost, implementation cost, what else? Overfitting. I mean, maybe the few examples that have gone astray are basically to be neglected because there's noise or there's just too specific to the data set. Okay, so I made a general statement. Yes, it's possible that this degree of thresholding, when to stop, you will decide yourself based on some validation set. Okay, so this is a basic idea, the top-down induction of decision trees. What you will do is pick in the main loop the phi I with the best decision node, best decision attribute for the next node, and the best is what we need to qualify slightly. We'll discuss this. We saw two qualities that the best decision attribute should have. So there is one more that is pending. So these are qualities of best decision we will see more of those. So one attribute is that the data skew or purity after splitting is greater than the data purity before splitting, and second is well, you will split only if there is good purity, when there is the purity is not good enough, right? So this is I would say broadly 3 characteristics of best. So there's a third that I want you to discover as we discuss further. So he's associating one possibility with purity function, which is called entropy. So entropy is one measure of purity. It's a good point. I'll make a note, but that's only one measure. Okay, so here but you've gone a bit too far to get to entropy. There's a much simpler notion of purity that you could come up with. So when I split on an attribute, right, let's say I split on this attribute, which class will I assign? When I split on an attribute, which class would I assign here? For example, if I say phi 1 equals R, which class would I assign here? the class with the highest probability, right? So what is the mistake I make when I assign that split or that branch to a class with the highest probability? What is the likely mistake I will make? The probability of the other class. If I decide that the majority class, the minority class will be the mistake I will make. So another notion of purity is 1 minus that mistake. So entropy is 1, and we'll see that. I mean, if you don't get it, it's okay. But another measure is 1 minus probability of less frequent class. And see, we'll see one more variant of these. So we'll see 3 variants of impurity. Okay. Huh? The probability of less frequent class is the mistake I will make.
So you want to
Purity, right? So if the probability of less frequent class is very small, close to 0, then I am almost pure.
probability is going to be the ratio of the count, right?
At that, yeah, in that branch. Yes, the probability will be the ratio of the classes in that branch.
Shouldn't that be compared with the current ratio? Like if currently it's say 1/3, and if the mistake is increasing, of course one shouldn't.
That's what I am saying. No? So the first criterion was that the data purity after splitting should be greater than data purity before splitting. Okay, so yes, his point is, what if we have only, what if we have 3 classes? So what will not work for 3 classes? So his point is this 1 minus probability of less frequent. Let's defer that. I mean, since this was brought up, I just made a note that there are other possibilities. So for the time being, this is just another possibility. We'll discuss that. Okay? We'll just wait. Again, we'll wait. So since the suggestion came from you all, I'm going to discuss this. But some notion of purity. Okay, now assign phi I as a decision attribute for node, and then for each value of phi I, create a new descendant of the node. Okay, we have done this for phi 1, and now all we are saying is the next step, you will now create, you will identify another phi prime to split on. You will do the same thing here. You will again measure the purity before and after and ensure that I pick that phi which brings about the greatest impurity reduction or purity increase. So in all processes you are basically sorting the training examples, so dividing the training examples to leaf nodes to the branches. If training examples are perfectly classified, then stop, else iterate over new nodes. I am just summarizing this picture again here. So we have a phi I, we have Vi1, Vi2, Vi3, okay, Vij in general. And then now we are talking about some data purity. So purity before, which is a property of the class distribution, and there is some purity associated with Vi1, purity associated with Vi2, purity associated with Vi3, right? Each of them gives you a purity. So one question was, what does a measure of purity such as entropy mean? Well, entropy, is it purity or impurity? I'll have to discuss this. But let's say the class distribution look like this at any specific node, and now we'll talk about multiple classes. When is the data pure? When the class distribution is highly skewed. Now what does entropy measure? Measure of uniformity, right? So if the entropy is high, it means that the distribution is largely uniform, right? Yes, high entropy means when is the highest entropy? When all classes have equal probability. Whereas purity demands the class distribution to be skewed. So you say, what would you want? Entropy or negative of entropy as a measure of impurity? As a measure of purity? Negative entropy. Okay, so entropy, which is summation over all the classes Ci of minus of PCi log PCi, okay, is measure of non-skewness or impurity. So entropy is a measure of impurity, not really purity. So you'll have to take its negative. And we'll see two other measures, but negative entropy, you see why it's a measure of purity. Now tell me, based on this simple depiction, is there a third point we are missing? I hinted that there are three characteristics. One is I want to use an attribute if it increases my purity. I gave an example of negative entropy as a measure of purity. But now there are three branches. There is a purity of Vi1, there is a purity of Vi2, there is a purity of Vi3. And I am saying that it should increase the purity. But there are three branches. Which branch should increase the purity?
Kind of expectation over all three. So average it according to the number of points.
Right. So look at this branch. This is pure. This has 4 points. This branch is not very pure and it has 5 points. This also has 5 points and similar kind of impurity. So a branch which is pure is still not convincing enough because it's in minority. So the purity or the measure of impurity or purity that we have should take into account the branch weightage, the number of points in that branch. Okay, that's the third point we were missing, and now we are all set to go ahead. Okay, so more the number of data points in a branch, more should it contribute to purity. A point with larger number of data points should contribute more than a branch with smaller number of data points. Okay, so question is, all this we are doing based on the training data set, but the query will not come from the training data set. How do you ensure that I am generalizing enough? Okay, we will come to that. So the regularization, and I like always, regularization is often an afterthought, right? So let's do our good work and then we will do an afterthought on regularization. We want to generalize. Well, it will work. See, the starting point, why would linear regression work, where we began the entire course with, right? The assumption is that the training data is a fair reflection of query points. It's a fair reflection. I mean, the play tennis example, your friend played tennis under certain conditions. I more or less would go by his trend, the trend he set. But I want to ensure that his bad mood is not accounted for in my decision making. Maybe he was just in bad mood for one entire month and he never played tennis despite being whatever, right? So then I want to ensure that I generalize across his patterns. But more or less we would like to borrow from the previous observations we made. Okay. So training data is always supposed to be fairly reflective of the query set or the test data. Okay. Any other question? These are good questions. So now I want to put all these together into one giant formula. So what would I do? Well, one is to look in terms of purity, but I will discuss in terms of impurity. Okay. What do you want? We want the maximum reduction in impurity. Right? When I say data skew or purity after splitting is greater than data skew before splitting, another way of putting this is data impurity after splitting is less than data impurity before splitting. Because entropy happens to be a measure of impurity, we can present the whole thing in terms of impurity. So data impurity after splitting is less than the data impurity before splitting. So I could talk in terms of impurities. So now I want to write my expression for which phi I to pick next. So can I say that I'll pick my phi I, which is the argmax over all the features, okay, phi argmax over phi I of what? So I'm asking for a general expression. What would I like here? I want maximum reduction in weighted impurity. So right, we want reduction, but I want the impurity contribution or purity contribution to come based on the weight. So so help me write an expression. Maximum reduction in weighted impurity. Don't give entropy. Entropy is a specific example. Impurity. Use impurity if you want. Yeah. So what will be impurity of? Yeah, but reduction, right? So impurity before splitting. So you want maximum reduction. So can I say it's impurity in the data set before splitting? You can reduce it, but yeah, I mean remove it. Fine, but let's just be faithful to what I've written here. Minus okay, so the general idea is that phi I, when I split, then the branch will have dv11 to dvij. These are the data instances. So I'll talk in terms of the data instances. So minus summation over all the j, right, or summation over all the vij's if you want, that that phi I can take, all the values phi I can take of size of the relative size of data into the impurity of that split. Is this what we would like? The branch will contribute to an impurity, but I will consider it as much as the weightage of that branch relative to the total size of the data. Okay, in plain text we are saying bring that attribute phi which brings about maximum reduction in impurity of the data subset induced by phi I, and just to be technically consistent we are saying maximum reduction, maximum expected reduction, expected or database weighted across all the branches. And that's what we have written on the board here. Okay, so there are different measures of impurity. So data gets split. You could think of, I've used S here instead of D, that's also fine. So S is the entire sample. HS is a measure of impurity of the sample. H is the entropy. Entropy measures impurity. And we give this entire difference, right? The entropy, for example, H before and H weighted H after. This is also called the gain. This entire expression is often called the gain. The gain. So you will split on that attribute which has the maximum gain. The expected reduction in entropy.
Here, this procedure is slightly greedy, right?
It's greedy. This is a completely greedy procedure, not slightly.
Optimal way to do it would be to consider each phi I, and for each of these sub trees you have to enumerate all possible subsplits and find out expectation on that full thing.
So the suggestion is, if you want to do it optimally, what you will do, you will not just consider just one level of branching. You will consider, well, if I branched here and then I picked an optimal branch thereafter and then I picked an optimal branch thereafter, then what would be the overall expected reduction? So that's what you should be doing ideally, but obviously that's going to be expensive. And sometimes greedy helps. Why? Because we don't want to take the training data all that seriously. I mean, optimal means that the training data is like absolute truth for me, which is not the case. So sometimes greedy helps you generalize. I mean, stochastic methods, right? They don't give you, they are applied on non-convex loss functions and neural networks. They don't give you the optimal solution, but then it also kind of helps you regularize. That's also been one of the hallmarks of advancement in AI, that suboptimal results have been used to our advantage in the sense of regularization, right? Okay, so there are other impurity measures also. As I said, entropy is one measure of impurity. I'm going to just this pure distribution is what we want, but what we have developed is a measure of impurity. So exactly what I wrote here, just that I have used S instead of D in the slides. Okay, and entropy we kind of discussed. I also discussed this, but for those who didn't understand, let me revisit the third example of impurity. So suppose I pick a branch, and in that branch I always assign the class which has the highest probability, right? So the error I incur is the probability of the wrong class. I mean I would say the less probable class, right? So impurity can be associated with yeah, so this is 1 minus probability of class Ci across all values of I. If I take a min, the class with the minimum probability, minimum value of 1 minus Ci, that will give you a measure of impurity, right? So let me erase this from here, because this was discussed as a measure of purity. I don't know where to write this, but let me erase this one. Okay, so let's take these three examples. So if what will be the value of min over I of 1 minus P of Ci here? I am looking for min of 1 minus P of Ci. So that will correspond to 2 by 5. No. Yeah, so min of, so you will have to look at min of 1 minus 3 by 5 and 1 minus 2 by 5. Min of 3 by 5 and 2 by 5 is 2 by 5. So that is the measure of impurity associated with this class. Min value of 1 minus probability of each class. So this kind of takes care of your concern. There was a concern expressed earlier when I just say 1 minus probability of the less frequent class. Your concern was, well, what about if you have multiple classes? So now we have solved that slightly differently. Okay, so impurity here as per this would be 2 by 5. As per this, the impurity here would be 1 minus 4 and 1 minus 0, min of the two, right, which will be, sorry, 1 minus 4 by 4 and 1 minus 0 by 4, right. So this will be 0, there is no impurity here, and this impurity is again 2 by 5. Okay, so makes sense. You can also have something called a Gini index, which is a quadratic form, which is somewhere in between the entropy and class min probability. And let's try and plot these three. Okay, the plot will help you understand these three. Okay, so let me just recap. This is entropy. Okay, this is minus of summation P of Ci log of P of Ci. The one in green is the summation over Ci, P of Ci into 1 minus P of Ci. And the one in red is min over I of 1 minus P of Ci. The max values that the three takes are slightly different. So both, so the one in green is called the Gini index. The one in red is called class min probability error, and this of course is the entropy. Okay, so entropy takes a max value of 1, whereas the other two take a max value of 0.5, right. 1 minus P of Ci at max can be, I mean, we have considered this for 2 classes, sorry. So this is all for 2 classes, plots are for 2 classes. So in the 2 class case, P of 1 minus P of Ci min will at most be 0.5. Okay, so both Gini index and class min probability error take the same max value. There is only a scale difference that entropy has. It can take a max value of 1. That is exactly when you have completely uniform class distribution. But the nature is the same. All of them peak at exactly 0.5, right. The peak value is here. The probability of fraction of class is 0.5. That is where all of them peak. And in some sense the Gini index and cross entropy, they pick up a much faster than not cross entropy, entropy and Gini index pick up much faster than class min probability error, but then they flatten out around 0.5. So which means that I don't want to consider 0.4 to be too different from 0.6 or 0.5. I mean, I want them to be treated at par. So there is this region of flattening out. Around half. Okay, so you can pick any of them, but Gini index is one of the most preferred. It kind of gets you the advantages of both worlds, entropy as well as class min probability error. Now we come to the last point of discussion here, regularization. Okay, so the problem is you will keep doing this, running this algorithm, pick the feature with the maximum expected reduction in entropy. You will keep doing this at every branch, the greedy algorithm, and what might happen in the process? One way is, okay, I will keep on building, catering to even one example. For every example I will build a separate feature splitting. So your decision tree can become very large, and large decision tree means overfitting, right? The whole idea of decision tree was so that I have very less bias. So you may say, okay, I'll try and make it very small, but small decision tree means very low bias, very high bias. So I don't want to be so biased that I hardly build the decision tree, and I don't want to have so much variance that I build the decision tree to any arbitrary level of depth. How do I balance between the two? So then there are some important points here. First is you must have a validation set based on which you decide how much to grow or how much to stop. Right, and the structural regularization is based on the following observations. So it's a structure, right? So it's about when attribute to be grown or not. So the following observation, they are too shallow would imply high bias or low bias. If I say I'll stop with one attribute, that will be high bias, very high bias. I'm biased towards too simple a model, right? It's high bias, right? It's like a linear. If I had always a linear regression fit, I didn't allow polynomial. So linear has higher bias than polynomial. But then what did we see with polynomial regression with very high degree? What increases? Bias is low, but then variance increases, right? So too deep, arbitrarily deep. I mean, instead of saying too deep, I'll say if you make it arbitrarily deep, will imply high variance. This is really overfitting. Like too shallow is a case of underfitting. Where you're saying, well, even trading data is not satisfied with me, what to speak of test. But overfitting means I have satisfied the trading data, but test I may have too much variance. So what would you do? What would be your regularization criteria under these observations? Yes.
If the decrease is too small, then don't accept just stop.
So here, higher the purity, less is the need to split. So split only if impurity reduction is significant, right? So let's look at possibilities. Split only if significant impurity reduction. Okay, so I say significant. Somehow it's not loading right now. I'll point you to the link, you can try it out. In my tutorial 10, I talked of, I have this section on hypothesis testing, right? So we say that hypothesis testing can be used as a stopping criterion or a pruning criterion. You can say that you have done hypothesis testing in your 2 and 5. No hypothesis testing? Oh, so then ignore. Anyways, this was optional reading. But you have a null hypothesis which says the distribution in the left branch or distribution here is significantly different from the previous distribution or not. So hypothesis testing is used for checking for such statistical, making such statistical tests. Okay, so I won't talk about it because you have not done it in 2 and 5. Okay, but that's one way. But then any other, limit the depth of the tree. But I must tell you that because it's greedy, if I limit the depth arbitrarily, it may happen. I mean, I wanted to show in that applet very interesting example. So sometimes what happens is the attribute I pick, let's say I pick phi1. Phi1 makes a very small difference in the impurity reduction. But suddenly the way phi1 infuses a distribution, phi3 starts making a big difference. Because the whole choice was greedy, I might pick a feature to split on which is not very interesting. So, but the effect this feature has is on other attributes which I pick later on, and they become very interesting, right? I mean, just to give a simple example, it's possible that, so it may be very difficult to differentiate students across branches in our institute. I mean, just based on CPI, every class will have a similar distribution, right? And or will you distinguish students based on their hostels which they stay? Again, I mean, I think after second year, you're all skewed, right? Everyone is distributed everywhere. So suppose someone came to the institute and wanted to find out which student belongs to which branch just by probing attributes, right? So it's possible that an attribute such as the building that a person goes to, that's the visiting pattern, the classes where they are held, that might give you an indication of which branch a student belongs to, but it may not be a big differentiator because you have electives, you have minors. But having chosen that branch, perhaps the projects that students do, the title of the project start becoming very interesting and becoming a big distinguishing factor. So often it happens that teacher chosen earlier on is in itself not very effective, but induces a distribution such that subsequent attributes start becoming interesting. So stopping early is not always a good idea. Sometimes you may want to grow the tree fully and then do what? Prune. Okay. I wish the applet worked. Applet would have shown you this interesting case. So grow tree fully as much as you want and then prune. And you are growing the tree as much as you want because since the algo is greedy, is myopic and greedy. Okay, so this is often the case. So you will build the tree all the way and it may happen that at these nodes the distribution at very low level nodes, the distribution is like 1, 0, 0, 1. Somewhere down you're just catering to one example each. So then you start pruning, saying, well, I'm not going to consider nodes with very few examples. Okay, so largely these are the ideas. So stop growing when data split not statistically significant. We already explained that. So significance tests are used. There are parametric and non-parametric hypothesis tests. But as I said, all this is optional. This is not part of the syllabus. You can grow the full tree and then post prune trees. So you may try and minimize the description length, which is like the size of the tree plus the size of the misclassifications due to the trees. These two put together is the description length. So evaluate impact on valid, and all this you should do in the validation set. So as I pointed out, all these are done best on the validation set. Pardon? So as I said, you will prove based on the length. So I want the length to be reasonable plus not just the length, the misclassification it incurs. So if I prune to make the length too short, I'll create too many misclassifications. So what is the additional mileage I get out of adding a unit to the description, the length of the tree, vis-a-vis the misclassification reduction. So I want reasonable misclassification reduction for every unit of description length to the tree. Pardon? It's all on validation set. A third possibility is you will convert the tree into sets of rules. Okay, so when I walk down a particular path, I can think of it as a rule. So let's say I have this node. So and let's say this is phi 1, phi 4 and phi 3, and the branches are taken based on S, O, and phi 4 is based on W. Okay, so I could interpret this branch as a rule, as one rule. So my rule would be if phi1 equals O and phi4 equals W, then, right? So I can kind of serialize the tree and create multiple rules out of it. So sometimes what is also done is you post prune each rule independently. Instead of pruning the tree, you treat it as a bunch of rules after building the entire tree and then post prune the rule. Okay, so lots of heuristics exist. We won't have the time to discuss these. Yeah, right. So the conversion to a set of rules can be very expensive. There are many reasons why people do this. One is this decision tree is putting constraint on how the rules look like, right? You're saying that there's a structure to the rules. But once you have the rules, once you have the entire tree, you may say, I want to do away with the structure. I want an effective classifier. So instead of pruning a node, because pruning a node means pruning away all the values that branch out from the node. If I prune this, all of this disappears. But maybe all I want to do is cut out one branch of the tree. But that will not be consistent with the decision tree. Yeah, so as I was saying, all of this have then a lot of discussion needs to go on how you should be very careful in the pruning of such rules, right? But this is just one branch of regularization. So I mean, I have these slides on how you could use decision tree for bagging and boosting, right? Bagging and boosting can be applied as much on decision trees as you have applied them on perceptron. Okay, so these slides are just for your reading. I'm going to, this model very similarly on the discussion that we had in the boosting. So this is just for your optional reading. Though boosting and bagging is certainly a part of the syllabus, but this is just application to decision tree. As I said, decision trees are attractive in terms of bagging and boosting, largely because they have very low bias. They offer low bias, but they can have very high variance. Okay, so that's all I want to discuss on decision tree. Okay, so it was nice teaching you all, and wish you all the best for your exams. Thanks.